Good afternoon, welcome, and thank you all for being here in person and online. Today, my design group and I will be presenting our concept design for a nuclear support vessel, or NSV for short. We will go over a brief team introduction, then go over the NSV's mission background and general characteristics, look at the hull form and the general arrangements, and then we will go into further detail on the mission systems, structure, weights and centers, stability, propulsion, maneuvering, electrical systems, and auxiliary systems. We will then finish with acknowledgements and questions at the end. This is the design team. Ben Ackerman from St. Louis, Missouri, has spent his past winter working at General Dynamics NASCO and hopes to pursue his education at a graduate level after Webb. Hank Wolf from Huntersville, North Carolina, worked at Stolt Tankers and hopes to pursue small commercial vessel design. Calvin Schmid from San Diego, California, worked at General Dynamics NASCO, like Finn, and hopes to pursue hydrofoil design. I'm Paul Farragut from Southport, Connecticut. I worked at Savage Marine this past winter, and I hope to pursue a career in commercial shipping. The idea for the NSV comes from a hypothetical container ship company who hopes to build and operate a fleet of nuclear powered container feeder service. To support this fleet, they created a spin-off company called HANK, which stands for Helping Assist Nuclear Carriers with a K. This spin-off company is to design, build, and operate a fleet of nuclear support vessels, whose main missions consist of basic support, nuclear fuel handling, nuclear coolant water handling, and responding to various emergency scenarios. Most missions will be conducted inside a port alongside the container ships, but most emergency response efforts will be held at sea in a presumed sea state 2 or less. In keeping with the spirit of the nuclear powered container ships, the NSV must prove to reduce its environmental impact when compared to similar support vessels of its size. Now going into the basic design. The NSV has a length overall of approximately 117 meters, has an installed power of 12.5 megawatts, which pushes it to a maximum speed of 15 knots. It has a service speed of 12 knots and a range of 1,500 nautical miles. The whole form is based off of a parent vessel, the Pacific Greylag, an offer supply ship currently operating in the Gulf of Guinea. This ship was selected because of its similar tankage requirements. Copies of the Pacific Greylag's general arrangement were used to make a basic hull outline. This hull outline was then modified to better fit the NSV's mission requirements. This included lengthening the parallel mid-body and increasing the beam of the ship slightly. The whole outline was then further developed and faired in Rhinoceros 7 using the Orca Hull Assistant tool. Further modifications were made along the design process of this vessel. These include the depth at the aft being slightly reduced to better accommodate thrusters, and the freeboard was increased to bring the work deck closer to the weather deck of the container ships. From this hull form, with the Orca Hull Assistant and a grasshopper plugin, a line span was generated. As we can see, the hull has a rather boxy shape, as a high block coefficient. This is to better accommodate the tanks, workshops, and processing rooms critical to the NSV's mission. An overview of the general arrangement can be seen here. This will only be a brief introduction to the GA, as we will go into further detail over the duration of this presentation. The engine deck houses the bow thruster room, main engines, and various tanks critical to the NSV's mission. The processing deck is an extension of most tanks and engine rooms, and also accommodates the nuclear wastewater processing room here in the aft and the steering room further back. The main deck houses main mission critical workstations, and storage rooms. The O1 deck, or the work deck, houses the main crane, a walk-to-work station, vendors, and basic firefighting equipment. The forward part of the O1 deck is the beginning of the accommodation block, which extends to the O4 deck, located here. We then have the bridge and a helipad, as helicopters are rather critical in most emergency response scenarios. I would now like to introduce Calvin to go into further detail about the mission requirements of this vessel.
Thank you, Paul. The main purpose of the NSV is refueling of a nuclear container ship. The fresh nuclear fuel and spent nuclear fuel is stored in an 8 meter by 8 meter by 6 meter box weighing 1,200 metric tons. The location of this nuclear fuel storage area can be seen here. The nuclear fuel storage area is located towards the aft to minimize risk of harm to crew, and in the center to minimize the risk of any spills making it overboard. The requirements also specify that the vessel will utilize a hose system for the supply and return of nuclear fuel and distilled and irradiated water, and the reactor spaces will be accessed through a 3 meter by 3 meter hatch on board the container ship. The hoses, weighing 1 metric ton per meter, must reach to the container ship's centerline plus 5 meters and must be fully supported by our vessel. To achieve this, we evaluated both a cable-supported system and a crane-based system, and ultimately we selected the crane system as it provides a safer and less complex operation for the vessel's crew. Another aspect of the nuclear support vessel's mission is the supply and return of cooling water to the container ship's nuclear reactor. We are required to store a minimum of 2,000 metric tons of demineralized water and 2,000 metric tons of wastewater. The tank locations are shown here. They are positioned low in the vessel to enhance stability and placed near the wastewater processing room to minimize piping length. The wastewater processing room is located in between the tanks, as you can see here. Another part of the NSV's mission requirements are to provide maintenance services alongside the container ship moored at a pier. To complete this requirement, our vessel has workshop spaces and spare parts storage. The workshop space is located in the circled region on the GA and is right underneath the weather deck. This allows the space to be accessed by a hatch. Within the maintenance workshop, you will find storage for small spare parts and all the normal machinery you'd expect to find on board a workshop, on board of the ship's workshop. This includes mills, lathes, drill presses, and a metal 3D printer for custom small part replacement. On the weather deck, we have dedicated space for large spare parts, which will be stowed inside of shipping containers. And a forklift is available for moving these parts and other equipment around the vessel. The NSV is also equipped to perform repair operations. These include defueling, dewatering, firefighting, and deployment of a 12-person damage control team. To defuel in an emergency situation where the container ships has lost a function of their defueling pumps, the NSV is equipped with an emergency defueling pump located on the weather deck, so it is ready to be deployed at a moment's notice by our crane. The NSV also employs a similar concept for emergency dewatering. Our vessel is equipped with marine salvage pumps that can be deployed into the container ship in the case of flooding. In the case of a fire on board the container ship, our vessel is equipped with 6 fire monitors, ensuring that they are always in range at any orientation our vessel might be in. In the case where additional assistance is required, our vessel can deploy a 12-person damage control team via a 6 degree of freedom fully motion compensated walk-to-work platform. This is a platform often seen on offshore wind support vessels. The walk-to-work platform also has capacity for lifting up to 300 kilograms of cargo, allowing it to move smaller parts if our main crane is already in use. I would now like to pass off the presentation to Finn.
Thank you, Calvin. With the NSV's primary mission now defined, we can now get into the ship's real meat and bones. Starting off with the ship structure, our class society, Bureau Veritas, provides us with some minimum values for structural members. These values were determined using various ship parameters as well as the expected pressure on the side shell and weather deck. These pressure values were found using the BV rules and were dependent on wave condition and other hydrodynamic forces. The minimum values we calculated for the section modulus is 2.86 cubic meters, a minimum side shell thickness of 11 millimeters, and a minimum main deck thickness of 9 millimeters. These values were then used as a baseline for developing our midship section. Some features of note in this midship section is the decision to be longitudinally framed. This decision was made as most ships of this length and mission type are also longitudinally framed. This section went through various rounds of iteration to ensure that our section modulus was adequate for the BV rules. Here we can see our midship section in greater detail. It should be noted that our side shell thickness is 11 millimeters and our main deck thickness is 10 millimeters. It should also be noted that our section modulus for our midship section is 4.11 cubic meters, which well exceeds the BV rule requirements. From this midship section, we could then start making an estimate of the weights and centers of the lightship of our vessel. This was done by breaking down individual components into the ship work breakdown structure, or SWIBIS numbers. The steel weight was estimated by using the steel density and then finding the weight per unit length at the midship section. This value was then interpolated out for the rest of the ship, and an estimate of the structural weight of our ship was determined to be 1,920 metric tons. The other SWIBIS groups were then broken down and weights were estimated where manufacturer's data was available, or they were estimated as best as we could where they were not. We then also added a 5% service margin to account for any changes in weights down the line or any slight inaccuracies in our estimation. This gave us a total lightship estimate of around 2,936 metric tons. From the weights and center from the lightship, we could then fully define our full load departure and full load arrival condition. The main difference between our full load departure and full load arrival condition is the various tank fillings. So when we're departing, our fuel tanks are full and our demineralized water tanks are full, as that is what we are bringing to these nuclear container ships. And then when we arrive, our fuel tanks are much lower and our wastewater tanks are full of the water we have taken from the nuclear vessels. The results of our weights and centers were all pretty acceptable. There was one area of concern, and that was the need to ballast in the full load arrival condition. This is due to both the wastewater tanks and the nuclear containment being in the aft of the vessel. This causes a slight trim by the stern, but this is rather easy to fix with some ballast in the forward compartments. Now that we have our weights and centers defined, we can start discussing the stability requirements and seeing if our vessel reaches them. So these are from our class society Bureau Veritas, and these mostly are concerned with the area under the GZ curve. So it was rather easy to compare these requirements to our own ship stability using general hydrostatics. So our output here, the GZ curve can be seen on the right, and the area under the GZ curve can be seen on the left. We were also able to make a script in GHS that compares our values to the values of what was required by BV, where a P indicates a pass and an F indicates a fail. So as you can see there, our ship did pass all of the BV requirements. So in addition to the intact stability, we also ran a damage stability case. So that was a floodable length curve. So this was also produced in GHS, and our ship handily met one compartment floodability. And as you can see here, we failed in 2 places on our 2-compartment floodability, but that is something that would be very easy to fix in future iterations by just slightly moving around our watertight bulkheads. I would now like to invite Hank up here to continue talking about the propulsion and maneuvering.
Thanks, Tim.
The NSV is mainly propelled by 2 electric-powered azimuth thrusters, shown on the right. The sizing for these units was determined using a parametric analysis of similar support vessels that travel at similar speeds. A whole trough regression analysis of our hull's resistance was also used as a secondary method. Both methods yield similar results. An estimated 2,400 kilowatts of power is required for a cruising speed of 12 knots and 6,000 kilowatts for a max speed of 15 knots. The installed azimuth thrusters have a combined power of 7,000 kilowatts. Two bow thrusters, shown on the left, are also incorporated into our design. They were sized using another parametric analysis and provide 56 metric tons of thrust. The NSV is equipped to perform dynamic positioning, DP, using the azimuth and bow thrusters. In addition to maneuvering, DP is incredibly useful when conducting operations alongside nuclear container ships. During emergency assistant operations, when the NSV is unable to connect to another vessel, the dynamic positioning will allow for safe deployment of the walk-to-work platform with the emergency response team. In order to power the propulsion and all the other systems on board, 4 Wärtsilä dual-fuel gensets are installed. These engines consume marine diesel oil, MDO, during normal operating conditions, and green methanol when operating under fossil fuel-free mode. The combination of the 4 engines is rated to provide 12.5 megawatts. This is well above the estimated electrical load of the NSV that will be discussed momentarily. The high power also allows the vessel to have a fully redundant power system, a requirement of our dynamic positioning. An emergency generator is also installed for powering vital loads such as emergency lighting and navigation. The NSV electrical system was developed by breaking down and estimating various categories of loads. Load factors for cruising, mission, and emergency conditions were assigned to all the loads. Mission operations are calculated to be the most power-intensive conditions at about 5,600 kilowatts. This is because of the pumps needed to transport nuclear fuel and cooling water to and from an adjacent vessel. The NSV has enough power to evacuate in emergency at maximum speed before the mission systems have completed shutting down. This additional power can also be used to support future loads. Here's a one-line diagram for the NSV displaying a more detailed breakdown of the electrical system. At the top, we have 4 gensets. These provide power at 6.6 kilovolts. This is the thruster's rated voltage as shown by the fact that they are connected to the same bus bar. The power is transformed to 480 volts to supply the larger machinery loads, and the emergency generator is also rated for supplying this voltage as well. Lastly, the power is transformed to 120 volts for the smaller lighting interceptor loads. In addition to the electrical system, numerous other auxiliary systems were considered in this design. These include ballast control, potable water generation, HVAC, deck machinery, and emergency systems. Special consideration was given to the MDO system. The piping arrangement is shown here, superimposed on a general arrangement. One thing I'd like to add is that the tanks for the MDO and our methanol are not touching the sideshell and have ample room. This concludes our presentation on the concept design of a nuclear support vessel. We'd like to extend our appreciation to all of our industry mentors. Ian Bush, Tenley Barna, Dirk Christensen, Andre Steinhaus, Tom Sullivan, Peter Wallace, Steve White, Tim Merzwicki, and they were all vital to the development of this vessel. A special thanks to Ian Bush and Steve White for being here today to support us. And finally, a thank you to Professor Golden for organizing this project and today's events. Without further ado, I'd like to invite up my teammates and answer any questions y'all might have. Yeah.
I noticed that you had quite a lot of margin on your impact stability line. I'm kind of wondering what was driving your beam at 26 meters is well large. So I was wondering if what was driving the beam. That's all.
Sure. So the question was, we have a pretty large margin on our intact stability and kind of what drove that. And to answer that, in our initial kind of concept development, we assumed that we were going to need a pretty wide beam based off all these kind of various missions that we're trying to solve at once. And then going through the whole design, the first couple spirals, now we see that we have a lot of stability and probably could use a little more draft. So in our next iteration of the spiral, we're probably going to lessen that beam a little bit to get our stability a little more normal and also get our draft a little better. And that kind of ties into maybe trying to fix the trim with that same kind of alteration.
Thank you.
Look back at your general arrangement, what considerations were given to decontamination or docking post-intervention for your personnel? So I assume they're going to exit your walk to work, and then where do they go?
I can speak to that. The right on the work deck or the ON deck, yes, we have a nuclear suit storage room and decontamination room. So the personnel would enter that room first, decontaminate, take the suits off, and the suits would get washed in that room.
And I recognize it's common with the walk to work system to be mounted on the deck, sort of in the middle of the deck on OSBs, usually because it's an afterthought, it's not designed that way. So why not integrate that better into your house, your superstructure, so that it's not so much of a walk from the accommodation space to the walk to work system?
So that we haven't really considered that. We much like on many OSVs, we put it on right at the end. So I think as we go into more of the detail, the design spiral, that's a consideration. Thank you.
And one more at the risk of asking too many questions. Can you go back to your one line diagram, please?
Yes.
Did you say you were DP class 2?
We were trying to get there. Yes, that is the goal. We currently have some of the redundant elements. This one line though, at this point does not show fully redundant everywhere, but we do have the powering and machinery space to support that.
I'm taking the opportunity now to say for most of the groups today, I've seen a lot of single transformers from your high voltage to your medium or low voltage system.
Yeah.
Which is obviously a single point of failure. So in your case, you're not going to be DP2. But for other groups, even if they weren't going to be DP2, it's a tremendous vulnerability. So I think everybody should keep that in mind as they make further passes on their designs.
Thank you. Brian?
Yeah, I'm interested to know what regulatory, or rather what regulations govern your design in regards to nuclear safety? Like, were you using DOE or US Navy standards in any way, or were those not considered?
Yes, so all the nuclear equipment that we were given was given to us in a black box by the client. And the only requirements that we were given beyond that was that the nuclear storage room was supposed to be at a minimum of 20 meters from the accommodation block for the safety of the crew. Ian?
It seems like the crane has to carry quite a load with that hose. Did you address any kind of impact it would have on yield?
Yes, so in the double bottom, we have an array of ballast tanks that can be ballasted to counteract any movements caused by the crane, and it would be automated with a computer to calculate the exact amount of ballast required for a specific load and the distance from the.
Also to add, we have wing tanks as well.
Yes.
Okay, online, there's actually, I won't go through all of it. There's an interesting discussion about the labeling of your engine room and machinery space. There was a couple of questions about where the engine room is positioned. So you might want to consider that on the GA, just I think it's just a labeling.
Okay.
Comment. But then there was one additional question asking about how is the nuclear wastewater being treated on board your vessel.
So the question is how are we treating the nuclear wastewater when we take it on? And the answer to that is we were given kind of a black box, a wastewater treatment room, and that's located at the midship, as you can see kind of in this image. We were given a power requirement and a volume requirement, and that's about all the information we have on the treatment room.
We did consult with some industry mentors though on kind of more specificity about the size and weight of that, just so that we knew that we were preparing accordingly for when we knew more about it.
That's everything online. Is there anything else first? Thank you very much.
Thank you.
Thank you.